Welcome to the Resource Allocation Decision Tool help video number 2. How do I rate the effectiveness of an option? My name is Terry Haines and I'll be walking you through this video. In the Resource Allocation Decision Tool, the ReAD-iT, we ask you a question that will be worded something like this. In ideal circumstances, based upon the evidence, what is your judgment of how effective this option could be in addressing the problem? Highly effective, somewhat effective, not effective, or harmful? In giving you this question, we're asking you about an idealized situation where you've been able to take an intervention that's been described in the literature and you've been able to implement it very well at your local healthcare service that has enabled you to maximize the value of that particular intervention. What we're really asking you to do in addressing this question is make a statement about the causal link between your intervention and an outcome. So here we have some fictitious examples that we'll use to help explain these concepts in this video. So, does drinking coffee X make people run faster? Y. Now we typically use the letters X to denote the intervention or the thing that you're introducing to try and change the outcome, and Y to describe the outcome. So we really want to know if your intervention changes the outcome. However, when we think about this first question, it's not particularly specific. So let's provide a bit more detail about this question. Does drinking coffee compared to drinking water reduce the time it takes adults to run 100 meters? Now, that question could also be similar to another question. Does drinking coffee compared to drinking tea reduce the time it takes adults to run 100 meters? When thinking about the resource allocation decisions that you have to make, there might be a very small, subtle discrepancy between the question you're asking and the question that the research paper that you're reading is actually asking. So, in this video, I'm going to give you a few keys to success with using research in making resource allocation decisions. The first key to success is to understand the questions you are asking and the question that you are reading. There may be important differences between the question you are confronted with and the question that a particular research paper has sought to answer. Now, those differences may lie in the patients or settings that the research was conducted in, the intervention itself, including when it was provided, how much was provided, how long it was provided for, what the comparison group received, what the outcome measure was, and other areas of this particular research context. Now, just because there are differences between your research question and the research question that the research paper is sought to answer, does not mean you should discard that research paper altogether. What I find is that each research paper gradually reveals a little bit more of the answer to the question you're posing, so it's important not to throw the baby out with the bathwater. So let's return to our question and the issue of causality. Does drinking coffee compared to drinking water reduce the time it takes adults to run 100 meters? How can we go about answering this question? Well, I could try and find a group of people who drink coffee and another group of people who drink water and compare how quickly they can run 100 meters. Unfortunately, if I make this direct comparison, there could be what's known as confounding, whereby even though I'm trying to look at the relationship between coffee drinking compared to water drinking on running time, there might be another factor here, and in these photos, it's age, which is associated with both the intervention and the outcome. So even if there's no actual relationship that is direct between the intervention X and the outcome Y, mathematically it will still look like it's the case when I collect my data, and that is because there is this confounding factor that is associated with both of them. So a better approach might be to recruit a group of people, say about 20 people, and give them an equal chance of being randomly allocated to either a coffee drinking group or a water drinking group, and then see if they go and run 100 meters faster under those conditions. So the second key to success with using research in making resource allocation decisions is that studies with stronger research designs are less likely to have confounded results. Randomized trials may not always be perfect, but they are less likely to give you biased or confounded results than other research designs. So I would encourage you to give them more weighting when you consider whether an intervention works or not. Other weaker designs that you'll commonly encounter in the health research literature include before and after intervention studies, where the same group of people are followed up before and after they've received an intervention, retrospective audits, case studies, and a myriad of other designs that could be used. So let's return to our experiment. Here we have 10 people who were randomly allocated to the water drinking group, who then ran 100 meters, and I timed how long it took for them to run that distance. And we also have 10 people allocated to the coffee drinking group, and here is how long it took for them to run their 100 meters. So in each group we had one person in the water drinking group who ran 100 meters in 11 seconds, two who ran it in 12 seconds, whereas in the coffee drinking group we had one person who ran it in 10 seconds, three who ran it in 11 seconds, and so on. If I plot the means for these two groups, here we have the water group, or for no coffee group, here their mean running time was 13.7 seconds, whereas for the coffee drinking group it was 12.3 seconds. The difference between these two means was 1.4 seconds. So does this answer my question? Does drinking coffee, compared to drinking water, reduce the time it takes adults to run 100 meters? No, it doesn't. All I know at the moment is that within my sample of 20 adults, those allocated to drink coffee ran faster than those allocated to drink water. So what do I need to do? I need to think about confidence intervals. Confidence intervals can be used to help extrapolate the results from our sample more broadly. Confidence intervals are a range of values that are so defined that there is a specified probability that the true value lies within it. Conventionally, we use 95% confidence intervals. So we are 95% confident that the true value lies somewhere within this range. Confidence intervals can be applied to the means of each group. Here, I've added in red bars the width of the 95% confidence intervals for the water or no coffee group, and also for the coffee drinking group. And what we see is that there is some overlap between about 12.5 seconds up to 13.5 seconds in the 95% confidence intervals for the two groups. So does this answer my question? Well, no. All I know at the moment is that there appears to be some overlap in the confidence intervals in the mean time taken to run 100 meters between those allocated to drink coffee and those allocated to drink water. So what am I really interested in? I'm actually interested in the 95% confidence intervals of the difference between the means of running times for each group. Now to do this I can use a statistical analysis approach called linear regression. That's not particularly important right now, but this is what happens if you run that data through a computer program. It will spit out an output like this, and it's this output that you might see in a table in a research paper. Here we have a difference between the means of 1.4 seconds, which is what we saw earlier. And if we look further along this line, we also see the 95% confidence interval of that difference between the means, and that ranges between 3 seconds and about a quarter of a second on the other side of the 0 mark. If we were to graph this out, it would look like this. Now, I've changed the direction of the 95% confidence intervals here to denote that we're comparing between groups. So the mean difference between groups was 1.4 seconds. The 95% confidence interval goes from negative 3 seconds to positive about a quarter of a second. If that 95% confidence interval crosses over the null value, the 0 line in this case, then we are not 95% confident that there is a difference between drinking coffee and drinking water in the broader population. That the true value might lie somewhere between this mark, where there would be a favouring of water, to all the way over there, where there's a strong favouring towards the coffee. So, did this answer my question? Well, sort of. All I know at the moment is that there is no significant difference between the effect of drinking coffee and water on the time to run 100 metres, based on my sample of 20 people's worth of data. Now, although there was a difference of 1.4 seconds between the means in my sample, I was not 95% confident that the true difference is in favour of coffee. Therefore, I might recommend that more research is required. So key to success number 3 is that larger studies are likely to have more precise estimates of treatment effects. Having more patients in a study will likely make the 95% confidence intervals very narrow, creating much greater certainty in where that true treatment effect might be when applied more broadly. I would also encourage you to not get carried away with trends in smaller studies, as we've just seen with our coffee drinking example. If we are not at least 95% confident that the treatment has had an effect more broadly, then it's safer to assume that there is no effect until more research is conducted. Now, what do we do if there is more than one study? Well, meta-analysis is a method which is becoming more and more common that allows us to combine results from many studies. It is a statistical analysis technique. This usually results in having 95% confidence intervals that are more narrow or precise. Here we can see our original coffee drinking study and its results. Now, if I repeated that same study 2 more times with another 20 patients, or participants I should say, and another 20 in study 2, we might get results that look something like this. A meta-analysis allows us to see what the overall result is as if we'd treated all 3 studies as the one study. So here we have our effect estimate, so we average out to have a difference of 1.4 seconds between the coffee and water drinking groups, but our 95% confidence interval is now much narrower. It goes from 2.36 seconds to 0.4 seconds on the negative side that favours coffee. So they run faster, the coffee drinkers. And there's a gap now between the null value of 0 for the difference between the means in the 2 groups and where that 95% confidence interval lies. So we are now 95% confident that there is a difference between the time it takes to run 100 metres between the coffee drinkers and the water drinkers, and that true value, if applied more broadly, would lie somewhere between about half a second and 2.5 seconds faster. Now, sometimes it's not as easy as this to combine the results from multiple studies. Sometimes you can measure the outcome in different ways. Now, say for example in the 3rd study, I measured time to run 100 metres not in seconds, but in minutes. It would be very easy for me to convert minutes to seconds using the conversion formula that 1 minute equals 60 seconds. However, for many health service delivery questions, the outcomes can be measured using different approaches and no conversion formula exists. Let's look at an example. Here we have a new question. Does providing group therapy reduce symptoms of depression in depressed adults after a 6-month period? We can conduct 2 studies to compare this control condition to the therapy condition. One study measures depressive symptoms using the Geriatric Depression Scale, short form. This is a measure from 0 to 15, where there's 15 questions and each question has a score of 1 or 0. The second study could use the Beck Depression Inventory, version 2, which has 21 items and a total score that ranges from 0 to 63. So each question gets a score of 0, 1, 2, or 3. Here is the result from our 2 studies. Study 1, using the Geriatric Depression Scale short form, had an effect size of a 1-point difference in this scale, whereas Study 2 used the Beck Depression Inventory and had an 8-point difference in mean scores between the intervention and control group. Both were in favour of the intervention, but the results are quite different. One way that we can try and combine the results of these 2 studies is to calculate what is called a standardized effect size. Standardized effect sizes allow us to make comparisons between studies that have used different tools to measure the same outcome. So the formula for a standardized effect size is shown here. It is the difference between group means divided by that standard deviation of the outcome measure. Because both the difference between group means and the standard deviation are expressed in the units of measurement that were originally used, these cancel out so that the standardized effect size has no units, which means that we can combine it between studies and not violate any of those algebra laws that we learnt in high school. So here we have the results of Study 1 and Study 2 expressed as standardized effect sizes. You'll note that in Study 1, the 95% confidence intervals now appear much wider. And that is because we have divided by the standard deviation in Study 1, and similarly we've divided Study 2's 95% confidence intervals by the standard deviation of the Beck measure in Study 2. We are now able to calculate a 95% confidence interval for these 2 studies overall. And here you can see that overall it's a 0.62 standardized effect size difference between intervention and control conditions, but it doesn't quite reach statistical significance because the 95% confidence interval goes over that null value just by a little bit, 0.02. So we are not 95% confident that there is a difference between the intervention and control conditions. Now, the good thing about standardized effect sizes is that there is a rather conventional way of interpreting them. A standardized effect size of 0.2 is considered to be small. A standardized effect size of 0.5, medium, and 0.8, large. These are arbitrary figures though, and Cohen himself recognised this when first describing them. But as you can see, when we try to interpret the results of this meta-analysis that we've just undertaken, that Study 1 had a small standardized effect size, or pretty close to a small standardized effect size, that Study 2 had a large standardized effect size, and that overall it's reasonably close to being a medium, or medium working its way towards a large effect size for the overall meta-analysis. Now, standardized effect sizes cannot be used for some outcomes. For measures that have a yes or no, or a binary 0 or 1 outcome measurement approach, this might include success or failure at a particular task, or if a patient returned to work or did not return to work, for example. standardized effect sizes cannot be used. For count outcomes, where you're counting the number of events a person has experienced, sometimes it's very difficult to use the standardized effect size here. And also for ordinal outcomes, quite often we see in surveys where people are asked to strongly agree or disagree with a particular statement, it's very difficult to use standardized effect sizes. For ratio-based effect sizes, we have a different approach. Odds ratios, relative risks, hazard ratios or incident rate ratios can be used for these forms of data. However, as you'll see from the example below, the null value that we used to have was set at 0 because this was a difference between means. For ratio measures, the null value is set at 1 because you're looking at the ratio between one group and another group. So when we try to interpret the results of effect sizes for ratio measures, we're looking for the 95% confidence interval to get completely to the left or completely to the right of the null value of 1, not 0. Indeed, ratio measures don't ever get to 0. The scale of measurement on the y-axis, on the x-axis, sorry, is logarithmic. So the distance between 1 and 0.5 is actually the same as the distance between 1 and 2. So key to success number 4 is that standardized effect sizes can help compare outcomes across studies. There are different ways that effect sizes can be expressed, however, so it's important to understand how they are different and how they are interpreted. So now we return to our original question. How do I rate the effectiveness of an intervention using the ReAD-iT? Why did we not just ask you to say whether there was a small, medium or large standardized effect size in asking you this question? Well, there are 4 reasons. The first is that there are not widely accepted interpretations for the ratio-based effect size measures. Second, there are other important ways of expressing effectiveness, such as the number needed to treat, which can also be taken into account when considering the effectiveness of an intervention. Third, the interpretation of an effect size requires further understanding of the context of the field of research. For example, in public health research, a mass media advertising campaign might need only a very small effect size to be tremendously effective. If you have interventions that have a broad reach, can access a large number of potential patients very quickly, then you might only need to have a small number of them receive benefit from that intervention in order to justify the cost of the intervention. Finally, the control and comparison condition can have a very large impact on the effect size that you've observed. Let's look at this a little bit more closely. Let's look at another research question. Does providing group therapy or individual counselling reduce symptoms of depression more in depressed adults after 6 months? We look at 2 studies, one of each intervention compared to a usual care control condition. Here, the group therapy study shows quite a small effect size, very close to the null value, whereas the individual counselling has a significant difference between the intervention and its usual care control group. So one might be tempted to interpret this as saying that individual counselling is better than control therapy, or at least better than usual care, whereas group therapy is not better than usual care. However, what if I told you that usual care in the control therapy study was intensive weekly meetings with their general practitioner, which in the country that that research was conducted in might be the usual care that depressed older adults conventionally receive. But the usual care in the individual counselling study was no intervention. So what we're looking at here in the group therapy study is really group therapy compared to a form of individual counselling with their general practitioner. Does that change how we interpret these particular studies? Well, of course it does. So it's always important to consider the comparison group and the context of the research where it was conducted. A control group that receives high quality care will lead to a smaller effect size than a control group that receives low quality care. And small effect sizes in some contexts can be more important than in other contexts. So that is why we have our question phrased in this manner. In ideal circumstances, what is your judgment of how effective this option could be in addressing the problem? We want you to use your judgment, following your reading of the research evidence and your understanding of the context of the question you are trying to address, to rate the intervention as being highly effective, somewhat effective, not effective, or harmful.